Today's computers work in a sequential way. Despite of the spread of multi-core and multiprocessor architectures, even in those architectures, parallel computations meet sooner or later, since they eventually get synchronized. Therefore, one can say that today's computer architectures perform computations in a sequential manner. Okay, you might still have some doubts about what I've just said, but how about the following one? Today, computers work in a deterministic way. Okay, you might say that sometimes your computer does not seem to be deterministic. It crashes sometimes, or it performs the same task differently. Even though, if we investigate the causes and effects, we can realize that today's computers are indeed deterministic. As programmers, we already know that random numbers we generate in our programs are actually not really random, right? They are generated from the computer's clock or even by a mathematical algorithm. Today, computers are not able to generate real random numbers. So, to sum up, our machines are deterministic today. However, sometimes you might hear some news about recent developments of brand new types of computer architectures. You have probably heard of quantum computers. As we all know, the quantum computer is not complete yet, and therefore it is not ready for practical use. But who knows? The quantum computer might become a reality in 5 years or 10 years, and then we might start to use computers based on completely different principles. What can the humanity expect from quantum computers? Well, they can be expected to work in a deterministic manner for real. That is, to perform parallel computations independently from each other. And by performing those parallel computations, a lot of them, side by side, we will be able to solve such computational problems which cannot be solved by today's computers. Well, in order to avoid replacing this learning material in 5 or 10 years, and more importantly, to avoid replacing your knowledge in computational complexity theory, in this learning material we need to target those new developments of non-deterministic computations. In fact, scientists have been prepared for the rise of non-deterministic computers for a long time. In the next section, you will get to know the non-deterministic Turing machine. Such a Turing machine can make random or non-deterministic choices during its computation. It can decide if to go on with the computation this way or that way, or in a third direction, and after that, those branches of computations will never be synchronized. They will be performed in parallel, independently from each other. This is the point. As mentioned before, certain computational problems become tractable by applying non-deterministic machines. What such important problems do we know? Maybe the most important such problem is called the integer factorization or prime factorization, which is a mathematical problem. Don't be scared. This problem has a strong practical relevance. Most of the cryptographic protocols are based on the problem of integer factorization. This means that the safety of our credit card or our bank account relies on integer factorization. Integer factorization is such a computational problem which is intractable for today's computers. Therefore, encryptions cannot be cracked in reasonable time. However, if we used quantum computers from now on, factorization could theoretically be performed in no time, and thus encryptions could be cracked in no time. Our bank account would not be in safe anymore. So I think this is a strong practical motivation for investigating non-deterministic computations, and this is why we are gonna deal with non-deterministic Turing machines in the next section. There will be an important question to answer. Is the non-deterministic Turing machine more powerful than the deterministic one? I think I've already told you the answer. Yes, it's more powerful. But how much more powerful? In the next section, we will search for an answer and we'll find it at the end.